Let's find the analog of the curl in general relativity. Let's start with the expression a mu nu, the covariant derivative of the vector a mu, and this is d a mu with respect to x nu minus Christoffel mu nu tau a tau. If we consider now a mu nu minus a nu mu, we get an anti-symmetrical tensor. Let's do it. From here, it is very easy to see that we would get dA mu with respect to x nu minus dA nu with respect to x mu. The term related to the Christoffel symbol doesn't appear because it gets cancelled due to symmetry. The symmetry is with respect to the indices mu and nu. Now let's also consider another anti-symmetrical tensor. Let's consider a mu nu first. An anti-symmetrical tensor in this case, so this will be anti-symmetrical, which basically means that a mu nu is equal to minus a nu mu. We start from an expression that we have already derived, that Einstein has already derived at this point. A mu nu sigma equal to derivative a mu nu with respect to x sigma minus Christoffel sigma mu tau a tau nu minus Christoffel sigma nu tau a mu tau. Now we will sum the three tensors obtained by cyclic permutations of the indices mu, nu, and sigma. What I mean is simply this. We're going to sum a mu nu sigma with a. Now we are going to do a cyclic permutation of a mu nu sigma. So we are going to move the indices from the right to the left. So I'm going to have here a nu sigma mu plus I'm going to do another shift from the right to the left. So I get a sigma mu nu. And now we just have to do some substitutions. So I have dA mu nu with respect to x sigma minus Christoffel sigma mu tau, which multiplies a tau nu, then I get plus minus Christoffel sigma nu tau a mu tau plus derivative a nu sigma with respect to x mu minus Christoffel mu nu tau. Then here I have a tau sigma minus Christoffel mu sigma tau. Then here I have a nu tau plus derivative a sigma mu with respect to x nu minus Christoffel nu sigma tau, which multiplies a tau mu minus Christoffel nu mu tau, which multiplies a sigma tau. Now, this seems quite scary, but actually several of these terms will cancel. So, for example, let's consider this one. Also notice that since a mu nu is anti-symmetrical, this is equal to minus a nu tau. and similarly for the others. But if we consider this term will cancel. Let me see, where is it? It will cancel this one. They are exactly the same if you take a look at them with the opposite sign. Also remember that the Christoffel symbol is symmetric with respect to these two indices here, sigma mu. So you get exactly the same quantity with the opposite sign. And then you have this term here, which will cancel another one of all these terms. In particular, it will cancel, let me see, where is it? It's here. It will cancel this term here, if you check. Quite easy to see. And then you also have this other term here, which will cancel this term. All in all, this expression will simplify quite a lot. So you will simply get that this is equal to the derivative of a mu nu with respect to x sigma plus derivative a nu sigma with respect to x mu plus derivative of a sigma mu with respect to x nu. Now, I'm going to derive other relations involving covariant derivatives. This is what Einstein does in the next part of the paper, in the next part of this paragraph. We start from a mu nu sigma, and by this I mean the covariant derivative of a mu nu with respect to sigma here, to the index sigma. So I mean derivative a mu nu with respect to x sigma, and then also we have to consider the other contributions given by the Christoffel symbol. So I have minus Christoffel symbol sigma mu tau, then here I have a tau nu minus Christoffel symbol sigma nu tau, which multiplies a mu tau. Now we are going to multiply both sides of this equation here by g mu alpha times g nu beta. So what we are going to get on the left here, we can simply define another tensor a alpha beta sigma, because we are multiplying by these two tensors, this tensor here, and this is what we are going to get. We are going to get a tensor with two upper indices alpha beta and one lower index sigma. So we define this tensor to be g mu alpha, g nu beta, a mu nu sigma. And then we have to do something similar on the right of the expression here. And in particular, this first term, I'm going to rewrite it like this. So I'm going to rewrite this first term multiplied by these two tensors in this fashion. D with respect to x sigma of g mu alpha, g nu beta, a mu nu, plus, then here I get a minus g mu alpha, derivative of g nu beta with respect to x sigma, a mu nu, then I get minus g nu beta, derivative of g mu alpha with respect to x sigma, a mu nu, then we get minus g mu alpha, g nu beta, which multiplies this term. So we get Christoffel symbol sigma mu tau a tau nu. And then we get plus minus g mu alpha g nu beta Christoffel symbol sigma nu tau a mu tau, like this. Now we are going to use another relation that we have already derived. In particular, we are going to consider dg mu nu with respect to x sigma equal to minus g mu tau Christoffel symbol tau sigma nu minus g nu tau, which multiplies tau sigma mu. And we are going to use this for these terms. So I'm going to substitute that expression here for these terms. Of course, I have to take care of the indices because the indices in this formula are different, but it can be done. It's easy to do that. So let's do it. We have a alpha beta sigma equal to derivative of a alpha beta with respect to x sigma plus g mu alpha g nu tau. Then we get Christoffel symbol tau sigma beta a mu nu plus g mu alpha g beta tau Christoffel symbol tau sigma nu times a mu nu plus, then we get plus g nu beta g mu tau, which multiplies Christoffel symbol tau sigma alpha a mu nu plus g nu beta g beta tau Christoffel symbol tau sigma mu a mu nu plus minus g mu alpha g nu beta, these are upper indices, times Christoffel symbol sigma mu tau a tau nu minus g mu alpha g nu beta, which multiplies Christoffel symbol sigma nu tau times a mu tau, like this. I have, as I said, substituted this formula here, in here, and in here as well. So it is quite tedious, quite boring, but this is what we need to do. And then we can see that this term here is equal and opposite in sign to this term here. If you take a look, then this term here is equal and opposite in sign to this term. So this expression simplifies quite a lot, and we get derivative of a alpha beta with respect to x sigma plus Christoffel symbol sigma tau beta a alpha tau plus Christoffel sigma tau alpha a tau beta. Now we found this formula, and in a very similar fashion, actually in an analogous way, we can also derive this formula A alpha mu sigma equal to derivative of A alpha mu with respect to x sigma minus Christoffel sigma mu tau A alpha tau plus Christoffel symbol sigma tau alpha times A tau mu. And now let's consider this formula here, which starts here, A alpha beta sigma equal to this expression. We are going to contract the indices beta and sigma. So if we contract the indices beta and sigma, on the left I will have only a vector with an upper index alpha, and on the right I will have to contract this expression here, and I can write it as dA alpha beta with respect to x beta plus Christoffel symbol beta tau beta A alpha tau plus Christoffel symbol beta tau alpha A tau beta. Now, if A alpha beta is antisymmetric, it's easy to see that this third term is zero, because this term is antisymmetric, this term here is symmetric, therefore we get zero. So A alpha can be written as dA alpha beta with respect to x beta plus Christoffel symbol beta tau beta, which multiplies A alpha tau. And also remember that in previous videos we derived an expression for this Christoffel symbol here with two indices contracted like that. Remember that this beta here is an upper index, this beta here is a lower index, and this can be written as 1 over square root of minus g, derivative of square root of minus g dx tau. And all in all, you get that you can rewrite this as 1 over square root of minus g derivative with respect to x beta of square root of minus g A alpha beta, like this. Now, this expression here that we have just derived is the expression for the divergence of a contravariant six vector. Why does Einstein call it six vector? It's called six vector because an antisymmetric 4 by 4 tensor has six independent components. That's why it's called six vector. And the six vector is A alpha beta here. Since it's antisymmetric, it contains only six independent components. Now we are going to derive the divergence of a mixed tensor of the second rank. We start from this expression A alpha mu sigma equal to derivative of A mu alpha with respect to x sigma minus Christoffel symbol sigma mu tau, which multiplies A alpha tau plus Christoffel symbol sigma tau alpha, which multiplies A mu tau. Now we contract the index alpha with the index sigma. On the left we have only a vector of this kind, A mu, whereas on the right we have dA mu sigma with respect to x sigma minus Christoffel symbol sigma mu tau, which multiplies A sigma tau plus Christoffel symbol sigma tau sigma, which multiplies A tau mu. Now, similarly to what we have done earlier, this Christoffel symbol can be written as 1 over square root of minus g derivative with respect to x tau of square root of minus g, and we can rewrite this formula as square root of minus g a mu equal to derivative with respect to x sigma of square root of minus g a sigma mu minus Christoffel symbol sigma mu tau square root of minus g a sigma tau, like this. Now we can rewrite a sigma tau in a different way. So let me consider this whole term where I'm going to rewrite a sigma tau. So I have the same Christoffel symbol sigma mu tau times square root of minus g, and instead of a sigma tau I'm going to rewrite g rho tau with lower indices, and then here I have a rho sigma with upper indices. And in its turn, this term here can also be written like this. We have g rho tau, and then we can rewrite the Christoffel symbol in this fashion. We have g alpha tau times the square brackets here. Instead of the curly brackets, I'm using the square brackets. We have defined this symbol previously. Square brackets sigma mu alpha times square root of minus g a rho sigma, and the product of these two tensors gives me delta alpha rho. Therefore, we can also rewrite this expression like this: square root of minus g a mu equal to derivative with respect to x sigma square root of minus g a sigma mu. Then we get minus square bracket sigma mu rho times square root of minus g a rho sigma. In addition, if a rho sigma here is symmetric, so if a rho sigma is symmetric, we get that minus square bracket sigma mu rho times square root of minus g a rho sigma can be written in this fashion. We know the expression for these square brackets. We have minus 1/2 derivative of g sigma rho with respect to x mu plus derivative of g mu rho with respect to x sigma minus derivative g sigma mu with respect to x rho multiplied by square root of minus g times a rho sigma. Since a rho sigma is symmetric, in this case, these two terms are going to give me zero contribution because we are summing over rho and sigma with a symmetric tensor here, a rho sigma. Therefore, these two terms will cancel. So we are left with minus 1/2 derivative of g sigma rho with respect to x mu a rho sigma times square root of minus g. Now we can also rewrite this term in another way. In particular, we are going to substitute a rho sigma equal to g rho alpha g sigma beta a alpha beta. If we are going to do this, this can be written like this. It's minus 1/2 derivative of g sigma rho with respect to x mu times g rho alpha g sigma beta times a alpha beta, and I should also multiply by square root of minus g. This is equal to square root of minus g times minus 1/2 derivative with respect to x mu of g sigma rho g rho alpha g sigma beta times a alpha beta plus 1/2 g sigma rho g sigma beta derivative of g rho alpha with respect to x mu times a alpha beta plus 1/2 g sigma rho g rho alpha derivative of g sigma beta with respect to x mu here times a alpha beta. This will give me, so this is equal to square root of minus g times minus 1/2 derivative of g alpha beta with respect to x mu times a alpha beta plus 1/2 derivative of g rho alpha with respect to x mu times a alpha rho plus 1/2 derivative of g sigma beta with respect to x mu times a sigma beta, and this is equal to, if you just check, derivative of g rho sigma with respect to x mu times a rho sigma times square root of minus g. Therefore, we can write the formula for this expression here. Remember where we started? We started from here, and we did some kind of manipulations. It's quite tedious, I'm aware of that, but this is where Einstein stops, and he tells us that we will employ these relations later on. He will use what he has done so far in the construction of the theory of general relativity. So this is quite abstract, but these relations are useful first to understand general relativity and how to deal with tensors, but they are also used in the theory. So that's why Einstein is spending a lot of time in the first part of the paper dealing with tensors and deriving these equations. Anyway, what he derives finally in this paragraph is that the square root of minus g times a mu can be written in this fashion: derivative with respect to x sigma of square root of minus g times a sigma mu minus 1/2 derivative of g rho sigma with respect to x mu times square root of minus g times a rho sigma. Alternatively, this can also be written in this fashion, because if you remember, we have just obtained another expression for this last term: square root of minus g times a mu equal to derivative with respect to x sigma of square root of minus g a sigma mu plus 1/2 derivative of g rho sigma with upper indices with respect to x mu times square root of minus g times a rho sigma with lower indices